The mass that we've been plugging into all of our equations is actually the rest mass. And what we mean by rest mass is the mass of the particle when it's not moving. If we were to go ahead and actually measure that mass with a particle that isn't moving, that rest mass is what we would measure. So when we've been writing down little m, what we're really saying is m rest. The implication there, of course, is that for a moving particle, its mass would actually be different. But that's not what we want to focus on in this section. What we're really looking at is what happens when you get together a whole bunch of different particles and cause them to form a single composite particle. How do the masses of the individual parts compare to the mass of the composite? So let's go with the example of an oxygen molecule. So it's made up of two oxygen molecules that end up getting bound together. And if we were to measure the rest mass of an individual molecule, you would think then that the rest mass of the O2 molecule would just be twice the mass of the individual atom. It turns out that's not the case. The rest mass, m rest of O2, is actually slightly less than two times the rest mass of a single oxygen atom. Now this number is actually very, very tiny. We usually don't see measurable differences in mass until we start talking about nuclear forces, but this at least gets the idea across. So how is it that the mass somehow disappears? We started off with this much, and when we put the two parts together, it's less. Based on what Einstein has told us, we know that energy and mass are equivalent. So what this is implying is that that missing mass must somehow be related to the energy of the system. So right here, I've taken the equation E equals mc squared for the rest mass, and then written it in terms of the energies of the individual parts. So here's the masses of the individual particles, here's the kinetic energies of the individual particles, and here's the potential energy of their interaction. Now, didn't we just say rest? This particle's at rest. How can we have kinetic energies if the particle itself is at rest? Well, even though the particle, in this case, say the O2 molecule is at rest, the parts inside can actually be moving around, and they can have some kinetic energy associated with them. So let's go ahead and draw a potential curve. And the effective potential curve for atoms frequently looks something like this. There's sometimes a little bit of a repulsive part, and that goes down to 0. So what happens is these two oxygen molecules approach one another. The separation between them gets very, very small. And if they get close enough together and they lose some energy, let's say they're coming in at this energy here, if they lose some energy, they can then drop down so that their kinetic plus potential energy is less than 0. As we know, this means that the particle is now in a bound state. If this kinetic plus potential energy is less than 0, we're in a bound state. Now, for these two molecules, if we just look at the energy associated with the sum of their two rest masses, so this is not exactly to scale, but let's say that this is the mass of an oxygen molecule times 2 times c squared. So this is twice the rest energy of an individual oxygen molecule. Now looking at this term right here, this is the kinetic energy of the individual parts plus the potential interaction between the two particles. We see that this has a negative value. K plus U has a negative value. So the total energy of this oxygen molecule is actually slightly less than the rest mass of the individual particle. So this right here, if we look at the rest mass times c squared for the O2, we're going to see that it's slightly less. So this is m rest O2 times c squared. Now there's clearly an energy gap between these. This energy was carried off somehow during the reaction. A lot of times a photon will be given off, or energy will be given off in the form of kinetic energy or whatever. So that energy was carried away, and that's what allowed these particles to enter the bound state. But the key here is that since this term right here, the kinetic plus potential energy, is negative for two atoms that are bound together, then the rest mass of the resulting particle has to be smaller than the rest mass of the individual parts. This section goes on to talk a little bit about nuclear binding energy, and you see the same thing with atoms that are formed of individual nuclei. For instance, with the helium atom, the nucleus is comprised of 2 neutrons and 2 protons, and then we have 2 electrons. And if you were to go ahead and add up the masses of these individual parts for our helium atom, you'd see that this sum of these masses is actually larger than the mass of an individual helium atom. The difference in energies are very, very small. We're talking on the order of 1% or less, so these values are very hard to measure, but they are there and they have implications. This energy difference that we see can be seen in terms of fission or fusion. The energies that are released are coming from these differences.